Have you ever wondered what holds the universe together? What prevents planets, stars, galaxies, and even ourselves from disappearing into the void? It might seem like an exaggeration, but everything that exists, from the smallest atom to the largest galaxy, is governed by just four forces. What's most surprising is that few people know all of them. While we go about our lives, these forces work in silence, shaping the cosmos at every moment. They make light reach our eyes and keep atoms bound together. They also trigger stellar explosions and influence the fate of the universe's expansion. Invisible, yet incredibly powerful, they are everywhere. In this video, we're going to explore each of these fundamental forces. We'll understand how they work, what science already knows, and what mysteries still remain. Understanding how they operate can transform the way you see reality. After all, the universe is much stranger and more fascinating than it appears. Despite everything we know representing a vastness of matter, science reveals something surprising. All of this is just a small fraction of what actually makes up the universe, about 5% only. This visible part, called baryonic matter, is made of atoms. In turn, atoms are formed by protons, neutrons, and electrons. At the center of everything are quarks, fundamental particles that form protons and neutrons. It might seem like a lot, but it's just the tip of the iceberg. The other 95% of the universe remains shrouded in mystery. About 27% is made of dark matter, something that doesn't shine, doesn't reflect, nor interact with light, but exerts gravity, like an invisible skeleton that gives structure to the cosmos. The remaining 68% is composed of dark energy, a force that seems to push the universe outward, causing its accelerated expansion. These two elements, although invisible, have real and measured effects. And the most intriguing part? We don't know what they're made of. To try to understand this reality, physicists developed the Standard Model, a theoretical framework that describes all fundamental particles and their interactions, with the exception of gravity. Within this model are quarks, leptons, messenger bosons, and even the famous Higgs boson, responsible for giving mass to particles. Thanks to this model, we understand how quantum fields work and how fundamental forces act in the microscopic world. But when we look at the immensity of the universe, we realize there's still much to discover. And this is where gravity comes in. Gravity might seem simple. After all, it's what keeps our feet on the ground. But actually, it's the most intriguing of the fundamental forces. Although it's the weakest among the four, it dominates the universe on a large scale. It shapes the movement of planets, makes galaxies collide, and determines the final fate of stars. Isaac Newton was the first to describe it with mathematical precision, through the famous law of universal gravitation. The formula is simple, but its impact is colossal. However, it was Albert Einstein who changed our view of gravity. Instead of a force between masses, he described it as the curvature of space-time itself. Imagine a heavy ball on a sheet. It deforms the fabric, and smaller objects around it are pulled toward it. This is the central concept of general relativity. Einstein explains phenomena that Newton couldn't predict, like the distortion of light when passing by very massive objects. The universe, it seems, is more elastic than we think. But there's a curious detail. Despite being so fundamental, gravity still doesn't fit into the Standard Model of particle physics. This happens because we still haven't managed to create a quantum gravitation theory that works fully. There's a hypothetical particle called the graviton, which would be the messenger of this force, just as the photon is for the electromagnetic force. But to this day, the graviton has never been detected. This opens room for new theories and raises an inevitable question. Is gravity really a force like the others? If you're listening to me now, you can thank the electromagnetic force. This force is behind light, radio waves, magnets on the refrigerator, and practically all electrical technology. Unlike gravity, which acts on masses, this force acts between particles with electric charge, like electrons and protons. Thanks to it, atoms don't collapse, there are chemical reactions, and you can turn on a light bulb. Its range is infinite, and it can be both attractive and repulsive. This makes everything more dynamic. In the quantum world, the interaction happens through the exchange of virtual photons, massless particles that mediate this force in electromagnetic fields. The electromagnetic force becomes extremely efficient, even at large distances. In fact, its equation is very similar to that of gravity, but with electric charges instead of masses. The famous Coulomb's law describes this with precision. When two bodies have electric charge, they exchange photons all the time, even without emitting visible light. This force is also perfectly integrated into the standard model of physics, one of the pillars of long-range interactions, along with gravity. But there's an even more interesting detail. Under extreme conditions, like in high-energy particles, the electromagnetic force unifies with the weak force, forming what's called the electroweak interaction. This fusion suggests that forces that today seem distinct may be manifestations of something greater and more unified. And when we talk about union, the next step takes us to the heart of atoms. If the particles inside an atom were Lego pieces, the strong force would be the superglue. It keeps quarks together, forming protons and neutrons. And it goes beyond. This force also keeps atomic nuclei whole, preventing protons from repelling each other because of their positive charges. This is vital, because without it, atoms would simply disintegrate. Without atoms, there would be no baryonic matter, no life, no universe as we know it. We are literally glued together thanks to this force. Unlike the electromagnetic force, which is mediated by photons, the strong force is carried by particles called gluons. They have a special characteristic called color charge. Before you think of rainbows, it has nothing to do with real colors. It's just a way physicists found to explain how quarks combine. They called them red, green, and blue, but they could have called them A, B, and C. The idea is that quarks need to combine these colors to form stable particles, like when you mix paints and get white. The curious thing is that gluons also interact with each other, which creates a confinement effect. This limits their range to incredibly small distances, smaller than an atomic nucleus. It's as if they were trapped in an invisible cage. And here's one of the most fascinating things in physics. Quarks are never seen alone. If you try to separate two quarks, the energy used in the separation ends up creating a new pair of quark and antiquark, like trying to tear an elastic band that regenerates itself. This process forms particles called mesons, like pions, which also participate in nuclear interactions. This property maintains the stability of the universe at the subatomic level. But even with all this force, there's another that, despite being more subtle, is equally essential for transforming matter. The weak force might not sound as powerful as the others, but without it, the sun wouldn't shine and life on Earth would be impossible. This force is responsible for processes like beta decay, in which a neutron transforms into a proton, emitting an electron and a neutrino. This occurs within unstable nuclei. It's essential for the nuclear fusion that feeds the stars. The weak force acts by changing the type of quark within particles. This makes it a true alchemist of the subatomic world. This interaction happens through very specific particles, the W+, W-, and Z bosons. Unlike photons and gluons, these bosons have a lot of mass, which drastically limits their range. We're talking about a distance about 1,000 times smaller than the diameter of a proton. Still, this force plays a crucial role in nuclear reactions and processes that occur in extreme environments, like the interior of stars or in particle accelerators. Without the weak force, up and down, quarks wouldn't transform. The evolution of matter would be frozen. Curiously, the weak force and the electromagnetic force merge at high energies, forming what we call the electroweak interaction. This shows that, under extreme conditions, like those of the Big Bang, these forces might have been one and the same. This discovery reinforces the idea that all fundamental forces can be unified in a single, deeper theory. The search for this theory is one of the great challenges of current physics, and when we talk about messengers of these forces, we enter the intriguing universe of gauge bosons. Every fundamental force we know has its messenger, a particle that carries this interaction between other particles. These messengers are called gauge bosons. Think of it this way. When you throw a ball to someone, you both feel the force of the throw, right? In the quantum world, it's similar, but instead of balls, particles exchange these messenger bosons. And here comes a fascinating detail. The type of messenger determines how each force behaves. The electromagnetic force uses photons, which have no mass at all. That's why it can act at enormous distances, like light from stars that reaches us. The weak force uses W and Z bosons, which are quite heavy. It's like trying to throw a bowling ball instead of a ping pong ball. It won't go very far. That's why the weak force only acts within atomic nuclei. These gauge bosons form part of the backbone of the Standard Model, helping to explain how fundamental particles interact with each other. But it's worth remembering that the model only incorporates 3 of the 4 known forces. Gravity, for now, remains outside. Even so, what has already been confirmed is impressive. The model's predictions have matched experiments with extreme precision. But as we'll see, there are signs that the universe still holds hidden cards. Maybe even a new force waiting to be discovered. The Standard Model of particle physics is a true manual of the invisible. It precisely describes baryonic matter, that is, everything made of quarks, leptons, electrons, protons, and all the messenger particles of the 3 forces we know well: strong, weak, and electromagnetic forces. It was this model that predicted the existence of the Higgs boson decades before being confirmed at CERN in 2012. Each discovery reinforces its credibility. Even so, it's still incomplete, like an equation that needs to be solved. The biggest problem is that gravity, one of the 4 fundamental forces, simply doesn't fit into the model. Despite dominating the universe on a large scale, we still don't have a definitive way to quantize it. Because its hypothetical particle, the graviton, which theoretically would be the carrier of this force, has never been detected, neither directly nor indirectly. Furthermore, the model also doesn't account for dark matter or dark energy, which together make up about 95% of the universe. In other words, the Standard Model explains a lot, but it doesn't explain everything. Even so, it's considered one of the greatest achievements of modern science. Every time a particle accelerator tests a prediction of the model, it's confirmed with impressive precision. But it's exactly this precision that's starting to bother some physicists. After all, if it's so right, why is so much missing? This restlessness has driven experiments around the world to look for anomalies, signs that there might be something beyond the Standard Model. And perhaps this something more is already beginning to reveal itself. Imagine dedicating decades to understanding the forces that govern the universe, and then an experiment emerges that puts all of this in check. That's exactly what happened with the Muon G-2 experiment, conducted at Fermilab in the United States. Researchers were analyzing the behavior of muons, particles similar to electrons, only heavier. They discovered that their movement in a magnetic field doesn't match what's predicted by the Standard Model. It seems small, but for physicists, this set off an alarm. What caught attention was the anomalous oscillation of these muons, as if there were a subtle force acting on them, a force that the current model simply doesn't predict. This raised the hypothesis of a possible 5th fundamental force. If confirmed, it could indicate the existence of a new messenger particle, or even a connection with mysterious dark matter. The physics world went crazy. After all, this could be the beginning of a revolution in how we understand the cosmos. For now, the results are considered preliminary. The data is strong, but not conclusive, and physicists continue collecting new measurements with increasingly precise instruments. The good news? We're alive at a time when science can literally rewrite the laws of nature. If this new force is real, the Standard Model will have to be expanded or even replaced. And this leads us directly to the greatest unsolved enigmas of modern physics: dark matter and dark energy. Dark matter is a silent presence that we don't see, don't touch, nor detect directly. But we know it's there. It prevents galaxies from tearing apart, even while spinning at speeds that, by the logic of universal gravitation, should make their edges fly away. This invisible matter seems to envelop galaxies like a kind of gravitational halo, influencing how visible matter behaves. It doesn't emit light or heat, and yet its gravitational mass is detectable. What makes everything more intriguing is that dark matter interacts with the rest of the universe only through gravity. It doesn't respond to electromagnetic fields, doesn't collide with other particles in the traditional way. That's why it completely escapes our common detectors. Scientists have already raised dozens of hypotheses about its composition. Could it be made of still unknown fundamental particles? Could it be some exotic type of meson, or something beyond what the Standard Model can predict? For now, everything remains in the realm of possibilities. Dark energy is even more mysterious. Unlike dark matter, which holds everything together, this energy seems to be pushing the universe away from itself, causing its accelerated expansion. as if space-time itself were constantly inflating, defying our understanding of gravity and general relativity. Could it be a new fundamental force, an emergent effect of something we don't yet understand? What we know is that it's shaping the destiny of the cosmos, and it could completely change the course of theoretical physics. When we look at the universe with more attentive eyes, we realize that everything around us, from the smallest particle to the largest galaxy, is connected by a delicate balance of forces. There are only 4 fundamental forces, and even so, they are sufficient to build the complexity of everything that exists. The Standard Model gave us a solid foundation to understand this functioning, but science itself already admits there are more things out there, much more, and we're just beginning to understand what might be hidden beneath the surface. Are we on the verge of a new scientific revolution? Could the 5th force, dark matter, or the long-dreamed quantum gravity be the next step? Questions like these drive modern physics, but they also invite us to reflect on something greater: our curiosity. It's the true force that pushes knowledge forward. And you, have you ever wondered how much of the universe still fits within your imagination? Or how much of the invisible laws are shaping your reality, even without you realizing it? If these ideas messed with your head, great, that's the goal. Here on the channel, our commitment is to expand your understanding of the cosmos in a clear, accessible, and profound way. So take the opportunity to subscribe to the channel, activate the notification bell, and follow the upcoming videos. There's a lot ahead, and each new topic can change the way you see the universe and maybe even yourself. After all, when you understand how the universe works, you start to see life with different eyes.